All right, students, today we're learning about wave-particle duality. It's pages 8 to 10 in the notes. All right, if light can be both a particle and a wave, can matter be both a particle and a wave? That's exactly the question that French physicist Louis de Broglie proposed. And well, he was right. We call this wave-particle duality. Well, let me highlight that. Here we go. Okay. The de Broglie wavelength is lambda equals h over p, where lambda is our wavelength, h is Planck's constant, and p is momentum, and you can use the equation for p. P equals, that didn't work, mv. P equals mv. Okay. Um, Note the wave nature of matter is only noticeable on things that are very small, subatomic scale. We're never going to see this for anything that's macro size that we see in our everyday world. All right, find the wavelength of an electron traveling at 1.5 times 10 to the 6 meters per second. So we use our equation, lambda equals h over p. H we just plug in. For p, we're putting in the momentum of that electron. We use the mass of the electron times the speed given. Plug all those numbers in, we get 4.85 times 10 to the 10 meters. For part B, you can try this and make sure you get the same answer for both of these. Same equation, lambda equals h over p, and make sure you use the mass of a proton. For letter C, we're doing a baseball traveling at 40 meters per second. All right, you can see the answer is 10 to the negative 34. That's really small. That's 0.00033 zeros, 114 meters. It's really small. We're never going to see any wave effects from a baseball because the wavelength is so small. You can try D if you want. So question number 2, I don't think that's the number. I think my numbers got messed up. Why don't we see the wave nature matter in everyday life? Because the wavelength is so small, we don't see it. Next one, recall the diffraction grading equation. Determine the diffraction angle for a beam of electrons. So we just use our d sine theta equals m lambda equation. Sine theta equals m lambda over d. Theta equals inverse sine m lambda over d. Everything's plugged in. You get 5.56 times 10 to the negative 4 degrees. All right, wave function. Even singular particles like photons and electrons can behave like waves. Each particle has a wave function, which works like a probability distribution of where you might find the particle. The wave function can be negative, which allows for destructive interference. However, there's no such thing as a negative probability of finding a particle. You take the absolute value squared to find the actual probability. All right, so if I have an electron, which is some distance from the nucleus, it actually exists in all of this space. But if you were to look for it, you would be most likely to find it here. That's what the probability distribution tells us. We're most likely to find it here, a little less likely here or here, and almost not at all on the edges here. Okay, here's another wave function. We'd be most likely to find the particle here or here, and we definitely wouldn't find it where it's zero, because if you take the absolute value squared of zero, it's zero. Here's an actual picture of a hydrogen atom, and you can see this is the electron. The electron actually takes up all of that space around the nucleus of the atom. It exists in all of that space, but if you go to observe it, all of a sudden it goes to a single point, like single point. Um, but before you observe it, it's actually taking up all that space around there. There's a really cool interpretation of how this works. Um, it's possible that the electron's taking up all that space and then all of a sudden decides to be there, or maybe another possibility is that the electron um, is in all this space here, and when we observe it, there's multiple universes, and there's another universe where you might find it here, or here, or here, or here, and every time you observe something, it splits into different universes. So that's a cool interpretation. If you guys want, if you ask, I can post a video about the multiple universes, many worlds theory of quantum physics. All right, here we have, well, when we observe them, they become amber particles of grain because they're amber waves of grain, like the song. and then when you observe it, it becomes like a particle. So that's that. All right. When electrons orbit the nucleus of an atom, they form a standing wave. And if you look at these two waves, you can see that one of them is a standing wave and one of them is not. The one on the right doesn't quite line up. So that really explains something. It explains the Bohr model of the atom. If you look at the orbits of the Bohr model of the atom, they depend on the wavelength of the electron orbiting the atom. The smallest orbit is the n equals 1 orbit. That's where it can make one loop around and be one wavelength. The next orbit is where it's two wavelengths in a loop around. The next orbit is where it's three wavelengths in a loop around. So the fact that an electron is a wave causes the Bohr model of the atom. It causes the energy levels that we know. It's all because of this wave nature of matter. Photon momentum. Photons are massless. They accelerate from rest to the speed of light with no force and instantaneous acceleration. However, they do have momentum, and we can use the de Broglie equation to find their momentum. Use solve for p equals h over lambda. I don't know what happened there. We can find the momentum of a photo of 632 nanometer red light. Um, is 1.05 times 10 to the negative 27 kilogram meters per second. One application of this is solar sails. We can actually build sails to let things fly around the solar system. The photons from the sun are going to push against the sail and push your spaceship. Here we go. Let's figure this out. The average photon from the sun is about 500 nanometers. What's the momentum? P equals h over lambda is 1.33 times 10 to the negative 27 kilogram meters per second. What's the energy of a single particle of light? We're using E equals hf. And then for F, we're putting in C over lambda. So hc over lambda, we get 3.978 times 10 to the negative 19 joules. If we have a 1 by 1 square meter solar sail, it will receive 1367 joules. So we can figure out how many photons that is. That's 3.45 times 10 to the 21 photons per second. How much momentum is that per second? It's 4.56 times 10 to the negative 6 kilograms meters per second, which is also newtons. It's also pascals because we're dividing by 1 meter. Um, so that's going to get pushed around. It's not a large acceleration, but it's free, so it's great. Okay, we got some questions here. You guys should answer the questions. So pause the video and answer the questions, then I'll go through them. The next one, which you can already see on the screen, when we speak of de Broglie waves, we're speaking of the wave nature of particles. As to why electrons orbit in only certain orbits, a compelling explanation views orbital electrons as standing waves, where the wavelength is one circle. Wave-particle duality is most apparent in analyzing the motion of an electron because it's really small, and the smaller it is, the more wave nature we see. We can't see it in any of these larger scale objects.